We are honored to have Dr. Andrew Fung with us today, and we sincerely appreciate him sharing his insight with our audience. In this webinar, we will learn what factors are fueling the uptake of PZT MEMS, why access to PZT MEMS manufacturing is especially important for early stage development and low medium level production, and how North American companies can now access the highest quality PZT films by engaging with an experienced product development firm such as AMFitzgerald and a top MEMS foundry. The presentation will be 40 to 45 minutes long, and there will be Q&A at the end of the presentation. You are encouraged to ask questions. I would like to introduce now Dr. Fung. Dr. Fung is Director of Business Development. Dr. Fung advances technology development agenda for MEMS-enabled microsystems. He has 20 years of multinational experience in industry teams and academic research. With broad awareness of integrated microsystems, his track record covers community building, technology innovation, collaborative research, fundraising, and mentorship. Prior to joining M. Fitzgerald, Dr. Fung was team leader of MEMS nanofabrication integration at CMC Microsystems. Dr. Fung has received his BSc in electrical engineering from University of Waterloo and PhD in biomedical engineering from University of California, Los Angeles. So without further ado, I would like to invite Dr. Andrew Fung to take the virtual floor. Please join me in giving him a warm welcome. The floor is yours, Dr. Fung. Welcome to the webinar.
Thank you so much, Dr. Qureshi, for that introduction and welcome. Great to be here with all of you and great to be back in a sense. So we're all here because I want to tell you about an opportunity you have to cut your time to market in half when it comes to PZT MEMS. I like to think of MEMS development as a mountain expedition, right? So you start at the base camp with an idea, and gaining altitude here means increasing in your technology readiness level. That means you prove through prototypes both the validity of your concept, but then you also start proving the manufacturability of your technology. The goal, all the way up at the top, is the summit. In this case, it's stable manufacturing production of a product that people are buying at scale. So if you are climbing this mountain, if you are climbing Mount MEMS, then AMFitzgerald is your Sherpa. We know the terrain. We've walked it many times over the decades. We know the resources that you need to survive, and we've helped hundreds of companies to navigate this mountain on their expedition to reach the summit. And we'd love to help you reach the summit too. So I want to just take a moment now with the first poll to know where you are. If Brent, you could cue that first poll question, please. Where are you on the MEMS development journey? Are you in ideation stage, proof of concept stage, maybe advanced prototyping, or you're already into foundry work, or you're already in production today? Take a moment, please, to fill that in. Brent, is that showing?
Yes, it is. So you just need the answer of first question.
Yeah, it appears to be working.
Okay. So I want to give you a forecast of what the next few minutes will hold here. I'll begin by introducing to you AMFitzgerald, who we are and what we do, and then talk about really the reason why we're all here, because there exists today a real market opportunity for piezo MEMS. Some of you may be working with piezo today. I want to show you technology in general, but really present to you the industry-changing solution that is the main topic of this webinar. As CAGR mentioned earlier, we'll reserve some time at the end for some discussion. AMFitzgerald has been in business for over 20 years now, with a headquarters in Silicon Valley in California. We're a MEMS product development company and focus really on custom emerging MEMS, high-value devices for high-value markets. We cover our services to design and prototype all the way up to manufacturing. We'll cover all that terrain that you need to get your MEMS product to manufacturing readiness. So our team will also prototype in the Marvell Nano Lab at UC Berkeley, also at the lab at UC Davis, for advanced prototypes and de-risking activities before it's transferred to foundry. One of the things that makes AMFitzgerald so unique is a global reach and strategic partnerships. You'll see in a moment that MEMS Infinity selected AMFitzgerald for an integrated design service. I'll talk about that more in a moment. We're also an ecosystem partner of Silicon Catalyst, which is a silicon hardware incubator in California. So all of our learnings from doing this over the last 2 decades was distilled in this book, which you can get from Springer today. Our services really span modeling and simulation, mask layout and prototyping, right through to packaged chips. But our core expertise really includes the process integration aspects, mapping your process to a set of known tools, whether that's in our prototyping lab or the set of tools in a foundry where it's destined. We'll design everything with a design for manufacturing philosophy with a view to the whole system and the integration that it needs with other components. So I want to tell you today about an opportunity for piezoelectric MEMS in some very key markets. I'll start with this view of data from Yole, and it shows the markets with regards to MEMS. So from 22 to 28, there's a 5% CAGR forecast here, and it's broken down by these market segments. Of course, the consumer one being the highest volume is also the highest revenue. Keep in mind these numbers represent just the MEMS slice of much larger markets. But the point here is that the overall trend of sensorization is pushing a multiplication and proliferation of MEMS devices, which is a real opportunity for all of you, whether you're already in the workforce or you're just getting ready to enter the workforce. A look at the different types of MEMS components here gives us a really interesting view, because in the overlay that I'll show you now, a number of these technologies have adopted or are adopting a piezoelectric form in addition to whatever form it first had. maybe a first generation device was a capacitive MEMS variant. And now emerging generations of these devices are adopting piezoelectric thin films. And that happens for a number of reasons, to do with performance gains that the market is demanding, or manufacturing gains that increase the yield and lower the unit cost for the manufacturer. These devices have been introduced into the market over a number of years already. The earliest ones being print heads and RF devices. Of course, these are in the highest volume because they're in the consumer market. And all these other ones, as we move to the right, are newer and now emerging micromirrors, microphones, microspeakers. So there's opportunity here, and there's growth as well, as you see by the magnitude of these upward arrows. I want to give you just a quick history of some of the earliest market successes of piezoelectric MEMS to give you an idea of when these occurred and what we're talking about here. The use of piezoelectric materials, namely aluminum nitride and PZT lead zirconium titanate, is usually taken to boost performance, to increase the sensitivity of a sensor or decrease the power consumption needed in an actuator, for example. One of the earliest and I think the most commercially successful example here is aluminum nitride devices used in mobile communication filters and resonators. So here, thin film bulk acoustic resonators enabled something like 1000x volume reduction in that component. It's really one of the key reasons why the technology was able to go from those bulky 1980s handheld sets that you saw in old spy movies to what we all now hold in our hands and in our pockets, the smartphone. So now this is ubiquitous, right? And this really requires a very controlled growth of aluminum nitride to get low permittivity for good yield and large voltages in response to small excitations. Secondly, in the maybe late 2000s, a company called Silicon Sensing Systems in Japan and UK introduced a gyroscope, but I think this was a third generation gyroscope, this one enabled by piezo MEMS. And in this case, the performance gains they were able to get by going piezo and the manufacturing gains they were able to get enabled this device to enter the automotive market for navigation. In addition, you have perhaps a household item here, the inkjet print head. Epson used PZT inkjet heads to pack very high resolution printing capability into its systems. So these are three examples of some of the earliest market introductions. But today, a new generation of piezoelectric MEMS technology is rising. And this is all enabled by the versatility of thin film piezoelectric materials. So here's three examples. Solid state speakers, such as this one in wireless earbuds by Creative. These silicon speakers are developed by XMEMS. Low-cost ultrasound imaging is enabled by a system such as the Echo Iris system. It uses a PMUT array to achieve very versatile and very high-performing imaging capability. I recently had the opportunity to demo this system at the Abundant Nexus conference, and it just blew my socks off. Really, really interesting technology. Tunable optics is another area that is taking great advantage of piezoelectronic MEMS. So Polite is one company that has a fast focus device that gives the user instant all-in focus at video rate. So a lot of opportunity is being realized as this technology is adopted in the market. So before we move on, I want you to fill in the second poll question, if you haven't already, about which kind of piezoelectric device is most relevant to your interests, right? It could be one of the ones that I just showed, or maybe something that's newer and upcoming, something emerging from your work. Take a moment to fill in that second poll question. Now, moving from piezoelectric MEMS in general, I want to focus our attention now on PZT, one specific piezoelectric material, and look at some of the challenges that face its development and manufacturing. So piezoelectric materials are fundamentally transducers that commute between electrical voltage or polarization to some mechanical stress. As an actuator, you can apply a voltage and then see a resulting film stress or strain. Conversely, an incoming signal like a sound wave can cause a deformation in the film, and that outputs a voltage signal that you can then detect in your electronic circuits. I want to show you how this differs from the earlier generations of capacitive MEMS. There's some very interesting and important distinctives to realize here. So the capacitive comb drive on the left in green is probably something that every MEMS engineer encountered in school during training in MEMS. Right? It consists at sort of its fundamental level of two interdigitated combs. One is movable and one is anchored. And when you apply a voltage here, the electrostatic forces between the fingers pull the comb fingers together. And so you have an actuation. Right? The governing equation here in a simple form shows you how the force here scales as a function of the number of fingers, the depth of the silicon or the comb, the height of these comb fingers, your applied voltage, right? And all these dimensions of your comb drive. So that means that in the capacitive comb drive case, if you want to increase your force, you need to multiply the number of fingers, and that will, of course, get you a larger comb drive and a larger die. And if you know about silicon processing, larger die means A, lower yield, and B, a higher unit cost, because you can't fit as many die on a given wafer. It's also very dependent and sensitive to deep reactive ion etching. Getting very defined, straight sidewalls is a challenge at scale. It's also prone to a number of failure modes. Anything that gets in here between these comb fingers can gum it up. And this really has an effect on the lifetime of comb drive devices. But if you look to the right here, piezoelectric drives have a fundamentally different architecture. And this gives rise to a number of really interesting possibilities. So there's three main types shown here, but by making use of the piezoelectric property, one can actuate an out-of-plane motion in this kind of cantilever style. By interdigitating the electrodes, you can achieve propagating waves, and this is another way of actuating out of plane motion. But then the piezoelectric ceramic also has an out of plane stress coefficient. And so there's the possibility of sort of a vertical piston configuration of an actuator here. This governing equation really depends on the simple piezoelectric properties of the film itself. It's not unlike the comb drive, it's not a result of the structure that you etch out of the material. This property is inherent in the film itself. So a stress will arise from an applied electric field, and the scale of that depends on the size of your dielectric, or sorry, your piezoelectric coefficient. Right? So this is, on the first order, the equation of the mechanical response of a piezoelectric actuator. So this means that if you design the MEMS correctly, you can achieve very large displacements with a relatively low actuation voltage and a relatively low footprint. You don't have to multiply many fingers. You don't need a large area film. You just need a film with very good, strong piezoelectric coefficients. Comparative to capacitive comb drives, it's temperature stable, shock resistant, resistant to a lot of these common failure modes. And very importantly, the film performance is scalable. So a very small piezoelectric element within bounds behaves the same as a large element. And so you don't need to, you can scale these things very small and make very compact die devices. And of course, that has a big impact on your metrics down the line as you look at manufacturability. So I want to focus your attention more a bit now on PZT. Aluminum nitride was the first piezoelectric ceramic to be used in a thin film format, in a MEMS format. It is compatible process-wise with CMOS, and that has made it commercially wildly successful in the mobile communication market because it can be easily combined on the die level with CMOS circuits. But more recently, advances in PZT thin films is opening up new doors to address even more markets. Comparatively speaking, PZT tends to be more suited for high throw actuators or high force actuators. It's very well suited then for wafer level or chip level integration with electronics. And now some very precisely engineered thin films can cover both sensing and actuating functions. So all of these are actual or potential applications of PZT. But as with any emerging material or highly engineered material, we find that technical challenges come along with it. So the two things that matter most with PZT manufacturing is its manufacturability and its performance. So we want thin film deposition to be reliable and uniform across the wafer. And we want each wafer to be the same, and we want each lot ideally to be the same. This is not trivial when it comes to PZT. The performance, mainly about the piezo coefficient of interest, also the permittivity, if you're interested in sensing applications, and reliability in the field. So there's environmental factors and moisture and stuff is relevant here. But what I've learned as I see the various PZT films out there is that PZT isn't PZT. What do I mean? Like every manufacturing source of PZT has its distinct profile. That's because its performance is a result of a multitude of factors. So the film stack really matters here. What substrate you're on, what the seed layer is, which metals you use for electrodes, all of that matters. The crystallinity, because you need lattice matching, you need to look at grain boundaries and control all these things, right? And because you're making a mechanical structure, of course, you need to know the mechanical compliance of your PZT film, but really the whole film stack. So at the end of the day, I'd sum this up just by saying that characterization and process control are critical if you're going to work with PZT MEMS. There's some secret sauce involved here. And so you need ways of measuring and controlling all of these parameters in your manufacturing process. That means a lot of expertise must be built up around these processes. But over the past decades, manufacturing capability has progressed a lot. So here are three of the more popular deposition techniques for PZT. ULVAC has a system, a cluster system that allows you to deposit the entire film stack, so the electrodes and the barrier layers and the PZT film itself, all in one system without breaking vacuum. Just a few months ago, Lam Research launched the PULSA system, which is a pulsed laser deposition system, and it has some very impressive performance. Sol gel deposition is an alternative that is used, for example, by Rome, and it involves building up the piezoelectric film layer by layer with this cyclical spin coating and sintering process. Where could you go to access this, right? Because of all the preceding factors, the expertise that's needed, the special equipment that's needed, PZT is not found in many places around the world. So you'll see the places where it is available in a commercial foundry setting. But most notably, I want to point your attention to the fact that in North America today, there is no commercial MEMS foundry source of thin film PZT. That's significant, and I think that is the point at which we can intersect CMC's roadmap, because they have recognized the importance of gaining access to PZT capability for its mission. The efficient manufacturing of PZT MEMS requires some very specific things, right? I think that the large MEMS fabs are very selective about their customers. So we see as AMFitzgerald, as your MEMS Sherpa, over the years, we have seen an unmet need for PZT capability at development stages. So you're talking also about small to medium volume production, and with the flexibility to support some ramp up to higher volume when that's needed. So the development phases of PZT MEMS requires that film and process to be stable. You want to avoid, if at all, if you can at all, the scenario where you develop your PZT MEMS process and design in one environment, like a university lab or a development foundry, and then when you're ready for the next stage, you have to graduate to a commercial foundry where you have to retune everything to that tool set and that material. R&D fabs, although they provide a way to work with PZT films, comes with this switching cost. So in our industry, a real game-changing solution would find a way to pair MEMS development expertise with some proven PZT manufacturing capability and offer a possibility of designing straight into manufacturing environment. Right? This would really lower the barriers of access, which is one thing that CMC is about. It would decrease the overall product development risk and time scale, speeding your time to market and shrinking your overall development costs. So this is the reason, these are the reasons that drove us to form an alliance with a foundry in Japan called MEMS Infinity, which I will tell you more about now. Together, we've allied to bring you an industry-changing solution for MEMS development in the PZT space. AMFitzgerald and MEMS Infinity have formed a strategic technical alliance. This was just announced at the beginning of this year to provide an integrated product development experience. So that means that a technology developer like yourself can interface with AMFitzgerald to access this manufacturing capability and expertise at MEMS Infinity. You get access to very high-performing PZT processes and materials that have a proven commercial track record. This alliance will use the proprietary PZT film data in the design process. So AMFitzgerald's engineers will design using actual foundry data so that its designs and modeling are true to life. And that will shrink the design test cycle overall. So this will unlock the commercial potential for this this technology, providing global access to a development framework for MEMS piezoelectric devices. The model that we formed in this alliance is not unlike the one that the CMOS industry has known for decades already. So in the 80s, the CMOS industry formed this fabless business model. I think you're familiar with this, right? So the design expertise was kind of separated from the manufacturing expertise, and the two worked as partners. So our alliance with MEMS Infinity seeks to advance the development of MEMS PZT in much the same way. The typical way that a fabless MEMS developing company would go about development is shown here, right? So feasibility, there's a design stage, a number of prototyping iterations here. And once you get your prototypes advanced enough, you then select a foundry. You transfer your design to that foundry, making any design adjustments along the way. Eventually, with a lot of time and effort, you end up with production. This is the path that we've necessarily had to walk with a number of our customers over the years with whatever type of MEMS they're working with. But with this alliance, we can really compact this down. Because of the close work that we have with MEMS Infinity, our feasibility assessment is accelerated. The design stage is accelerated. We prototype directly at the foundry on those manufacturing processes. So that means these two steps in dark blue here, they drop out. There's no expensive foundry selection. There's no redesign for the destination foundry. We can head straight into pilot production. And this overall can shrink your time to market by as much as, I'd say, half. So at this point, I want to introduce you more to our business partner, MEMS Infinity, so that you can see into their capabilities and how we work with them and why. Now, I have to say up front that normally my colleague from MEMS Infinity would be here presenting this material to you, probably in a better way than I can achieve. But of course, because of the time zone alignment with Japan, that falls to me today. But the history behind MEMS Infinity is really tied into the history of Sumitomo Precision Products. They are a long-standing Japanese manufacturer that was founded in the 60s, first in the aerospace industry, but have been in MEMS for 30 years. I talked earlier about the importance of expertise and how that's regional. The expertise for PZT in Japan has historical roots because it was invented there in 1952. In 2023, last year, Sumitomo Group launched MEMS Infinity as its foundry service, both on 150 and 200 millimeter wafers, offering full foundry capabilities. And it was at this point that they selected AMFitzgerald as a front-end design partner. This is their fab in Amagasaki, which is receiving investment and expansion. The piezoelectric third generation MEMS gyroscope that is manufactured there makes use of PZT. So this material and process is really commercially and field proven. It's been functioning in the field for many years. The core capabilities of MEMS Infinity is not just the wafer production capacity, but the in-house deep knowledge of processing equipment. So the larger Sumitomo Group also manufactures processing equipment for used in MEMS, so deep etch and film deposition. And MEMS Infinity engineers have this track record and experience of developing product, such as just two piezoelectric examples shown here for micromirror and gyroscope. The test the test capability they have for their PZT film is quite comprehensive, both X-ray fluorescence spectroscopy to look at the elemental composition, along with EDX, also a number of optical and surface profilometry techniques, and laser microscopy, and of course electron microscopy. The unique aspect that you will be able to reach into here by working with our alliance is access to MEMS Infinity's world-leading PZT lineup. So they have two flavors of PZT, an epitaxial and a polycrystalline PZT. And these have been engineered to and tuned to span both actuator, transducer, and sensor applications. The polycrystalline PZT film has a high D31 coefficient, and the epitaxial PZT film has been tuned to have a low permittivity suited for sensing applications. And you can see how this figure of merit compares to some of the other commercial options out there. For those of you who are working in this area, you know that, like I said earlier, PZT isn't PZT isn't PZT. This table of figures of merit and metrology data, this is, if you're not a piezo MEMS designer, this may not be so relevant to you immediately, but these are typically the parameters with which designers need to grapple as they put together their concept and device. So this we don't have time to go in depth in, but if there's any questions later on about that need to look under the hood about these, then I'm happy to entertain that or connect you with a colleague as needed to do that. But those who work with the Alliance will get an integrated product development experience. right? All the way from concept to volume fabrication. And we'll work in this sort of multi-stage or multi-phase manner just to contain the risk, bite off a chunk at a time, and being able to plan out the roadmap of investment that's needed here. Phase one will start with a feasibility study, an understanding of what you want to do, why you want to build it, if that's the right thing to build, and then we'll step up through these stages, right? And you'll recognize these stages from the first slide. This is climbing the mountain towards the peak of Mount MEMS. We'll guide you through this whole process and work closely with the foundry MEMS Infinity along the way. Together in this alliance, we are opening up doors that didn't exist before to get PZT MEMS products into these new markets, into your hands. And I think working with you is going to be really exciting, because I know that in this audience are people who will be driving the development of the next generation of PZT MEMS. With that, I would like to thank CMC Microsystems for inviting me to your stage. I want to talk to you. We can do that by meeting at Hilton Head Workshop. That's coming up. Or feel free to write to me at this email here. Connect with AMFitzgerald on LinkedIn. You could also look into the MEMS product development book by scanning this code on the left. I want to end just by inviting you to reach out and make contact with me. I want to offer you completely free consultation with an engineer. If you want to talk about your idea or what you need, even if you don't know what you need, but you know where you want to go, we'll help you figure that out. So the third poll question that I will just close with here is, are you ready for a discovery call? Do you want to talk now? You can click yes, let's talk, and I'll get in touch. Or hold on a bit, we'll talk soon, but I need to organize some things first. Or maybe you're not ready. Whichever one it is, let me know. And I'm happy to hear from you. I'm happy to start a discussion with you about your journey in climbing Mount MEMS. So with that, I'd like to wish you all the best in your technology development efforts. And now we'll move to a time of Q&A.